So you've probably all heard of the singularity, that point where a powerful superintelligence would qualitatively surpass all human capabilities, and where our superintelligent machine overlords would either kill or enslave us, or cure mortality and disease and deliver heaven on earth. The former vision is expressed in the story of the child who asks her father, "Father, is the singularity going to happen before I die?" Father says, "Yes, right before." But we're not talking about that kind of artificial intelligence, a strong artificial general intelligence. Rather, we're focusing here on what's happening now, or narrow or weak AI. What's happening now, or maybe in a 3 to 5 year time frame, rather than a 30 or 50-year time frame. I'm just going to quickly introduce the panelists, but check out their bios in your FiRe booklet. Tom Conte is founding co-chair of the IEEE Rebooting Computing Initiative and a professor at Georgia Tech. Lorien Pratt is chief scientist at Zoolingua. For 35 years, she's been delivering AI in various forms. And Joseph Smarr, senior staff engineer at Google, working on all manner of things that relate to this topic. We're already surrounded by narrow AI, depending on how you define it. Anything from your anti-lock brakes to the Google search engine or Alexa. Your smartphone is a little AI factory. So how do we define AI? Of course, that depends on how you define intelligence. Tom, how would you define AI?
Well, not what we're calling it now, okay? I think that, I've lived through 2 AI winters, and AI was a bad word when ML, machine learning started to evolve, and I cynically think that they picked the term machine learning specifically because it wasn't AI, and now that it's become a marketing term that you don't often hear machine learning, they'll first say AI. I believe Google will advertise that they're doing AI, not machine learning. So I think we're far from that, but I think what we have been able to do with models of computation that ape at least some aspect of how the brain works is truly astounding.
Lorien?
I think AI, unlike wood or stone, is not a well-defined term and never will be, right? It's constantly shifting. So from a practical point of view, AI is the word that people use when they say, "Hey, Lorien, I need an AI solution." And there's as many definitions of AI as there are ideas in people's heads. So I don't like to pin it down, but I know it gets me work, so there we go.
Joseph?
Yeah, I mean, we generally, when we talk about AI, we mean software that learns and adapts as opposed to being hard-coded with the particular rules that it needs to work. And there's just so much data in the world right now, so much complexity, people need so many different things, and so it's just not practical to sort of hard code every single if-then statement that the machine might do, and it's not practical. The systems get sort of too big and too complicated, and so there's a variety of different techniques and details, but I think you just see in more and more of your life that in order for technology to be helpful, to actually know enough about you and to be able to do the right things, it has to learn from data, both at kind of the global scale and at the personal scale. And so I think that's why we're seeing it more and more in our lives.
So technology that can adapt without necessarily being explicitly programmed to do a particular function?
Exactly, yeah.
I mean,
how can you say that? Sorry. But I mean, don't you take it in the back room and train it? Isn't that programming in essence?
But you're not programming the specific things to do. You're programming it in the sense of look from these examples, try to figure out how to generalize, try to figure out how to maximize some function, right? So
it's really fundamentally different. You're not writing code. You're giving examples, and that's a really different activity.
I mean, to take a specific examples, we've made a tremendous progress in speech recognition and machine translation between 2 human languages. And it's ironic because the previous generations of the systems had huge amounts of humans hard coding in little features and little heuristics and little rules, and partly because we didn't have enough data and the algorithms also weren't as sophisticated. And now that we have these deep neural network-based algorithms, not only we can feed them a lot more data and they can actually take it in without overfitting. And so that's one of the big reasons these systems have gotten so much better. But honestly, the last few years have been us systematically scraping away the barnacles of all this stuff that the humans added in that's just getting in the way now, and letting the machine learn more end to end. So it really is pretty phenomenally different in terms of the actual practice of how we build and maintain these systems.
And if I could just underline that, you know, I kind of punted on the AI definition, but what's exciting about AI, whether you call it that or not, is I just want to underline what you just said. All you need is a list of examples. So here's a bunch of stocks, and then did they go up or down in the following 3 months? Here's a bunch of historical health data. Did this person get a disease in the next 3 months? If you can get a big database, it's just like, forget about a database, just one table, right? Where you have some historical data and then a label on it. With Zoolingua, it's an image of a dog, and then is this dog anxious or not? That's all you need. You just learned everything, 90% of what you need to know about AI, right? Is you just need this great big list of input, output, get 1 million of those, stick them into the magical engine, you know, use smart people like Tom or Google, and they'll build you an AI model that does performance that you've never seen before. And I know that sounds kind of crazy, but that is what it does, right? I mean, I'm not exaggerating.
Let me defend my comment. What I mean is that there's still a step where you're training the machine, whether you're training it by programming it in C++, or you're training it by using labeled data, there's still something here, and then you have a run mode here.
That's true.
And in a lot of ways, I don't think a lot of the public understands that when we talk about AI, we're really talking about something that was trained in the back room.
Right.
And when we're using it, we're really doing this other completely different, well, mostly
Although
different
even
process.
that is really changing, right? I mean, both in these traditional kind of supervised learning paradigms, any real production system is constantly having to be retrained based on live data that's going on. So if you think about a system like YouTube recommending what video you might want to watch next after you watch an existing video, that's a good example of a system that has gotten so much better because of the use of machine learning, but it's really incredibly important that it not get stale, right? And so it's sort of constantly taking the logs of what people are clicking on and what they're watching and figuring out how to sort of tune itself. And so the boundary gets a little bit fuzzy, and it gets even fuzzier when you look at these reinforcement learning-based systems like AlphaGo or some of these, where it really is just out there playing and trying things out and making mistakes. And I mean, that's kind of how we all learn in the real world, right? There isn't necessarily a discrete training step and a performance step, but you're kind of constantly trying to see what you did and whether it worked or not, and then decide what you want to do differently the next time. And I think we're going to continue seeing that kind of trend.
But to reinforce what Tom said, there absolutely is different compute requirements. So I'm running a system right now in some cornfield in Iowa that's got like 60 CPUs all like training and doing the magic brain Marvin thing. And that requires huge, you know, right now it's cloud compute. But then when I deploy that, I can deploy it on my phone.
Right.
And so it's really important to distinguish those two situations, the learning phase, which requires, you know, a lot of power, and then when you have that model that comes out of the learning, then it's very easy to deploy, unless you need to do that constant online stuff, which requires more compute.
And
So
let me pick on AlphaGo, if I can. Because here's an example of the incredible inefficiency in what we're calling today our success story in AI. And so if you look at, let's say, the second one, where they competed against a level 9 champion and they won 4 out of 5 times, which is fantastic. But they're using servers and they're using compute power that's in the tens of kilowatts against someone who's thinking as hard as he can is probably using 20 watts. I mean, that's
Power inefficiency is definitely orders of magnitude away. Now, the actual compute efficiency, one of the things that's so amazing about AlphaGo is that the successive versions not only performed better, but they used far less compute resources. So especially using TPUs, they were able to shrink it down to a much smaller number of TPUs. And it's not doing the kind of brute force look ahead the way Deep Blue did for playing chess. It's actually not examining that many moves, certainly probably more than the human is doing. And it's certainly burning a lot more electrons to do it.
But it's more just smart pattern recognition, the deep look ahead.
Yeah, it's this combination of these neural nets that have trained to figure out how to read the position of a board and figure out the value, and then to be able to guess what to do based on the situation. And you know, those are cases too where it's now the AlphaZero versions are learning from scratch without even knowing anything specific about the game of Go. So it's a pretty general engine that can learn multiple different games just by watching and playing. And so I mean, I think that's surprised even the people at Google and elsewhere in the AI industry that, you know, often we get said, oh, we're too, you know, utopian or whatever, too optimistic about these things. But we keep being surprised ourselves with how well this stuff is going. So that's one of the reasons why we stay, you know, pretty focused on it.
okay, with TPUs now maybe 10 kilowatts.
So that
but
sort of, that sort of points to, you know, 3 different areas where we can kind of assess the state of the art and what our near-term challenges and opportunities are. There's the hardware,
right.
And then there are the algorithms, and then there are the data sets that they're working on. And I think Dennis the first night talked about 10 to 100 trillion sensors,
Right.
and nobody has a data set like Google. I mean, and it's refreshing and changing, by the second. And even if the hardware and the algorithms don't change, you're going to get better results just from better and bigger data sets.
Certainly, but it's not just the quantity of the data; it's also the quality. One of the things we've really found is that tuning algorithms by giving them better quality data, like for example in image recognition, right? You take photos and Google Photos can tell you if it's a cat or what kind of dog or that kind of thing. One of the things that they did that really helped to get better was being very careful at when it would make a mistake, they could actually trace it back to which labeled examples got it confused, basically. And in many cases, they're kind of poorly drawn, or they're kind of ambiguous, or maybe there's just outright errors in the data. And by kind of cleaning the data more carefully, it's like if you gave a kid sort of confusing examples in school and you kind of got the brain off on the wrong track kind of thing. Right? If you can erase that and go back and give them a really clean set of data, they'll do a lot better even with the same total amount of data and with the same algorithms. So have you seen this in a lot of the medical context as well? A lot of these AI advances in medical imaging, medical diagnosis, if you can really get high quality training data, then you can do a lot better. And so that's definitely a focus.
It seems like in a lot of these areas, one of the challenges in AI is for the machines to understand context. And you mentioned speech recognition. Understanding the words is probably relatively easy, although given the ways people speak, that's a challenge. But in terms of understanding the meaning, the context is the real challenge.
That's right. And one of the big gains in speech recognition has come not just from having better models that can take an arbitrary bit of sound and try to figure out what it is, but it's like in the Google Assistant that I work on, we know if you're talking about call so-and-so, we'll bias the speech recognizer to look at your list of contacts and figure out the names of those. Or if you're trying to say play such and such song, we'll bias it to the list of songs we know about in our database. Or if it's a follow-up question, if we said, was that 9 a.m. or p.m. or okay, do you want to confirm it? We can bias the a.m., p.m., yes, no, that kind of thing. And humans do the same thing, right? We have a lot of top-down priors that help us take in noisy data and figure out what was meant. So the context helps a lot.
If the person requests play Girl from Ipanema, is it play the song Girl by the band Ipanema?
Yeah, there's still a lot of ambiguity.
Still got to know some context.
But let me add to that context. I think we're going to hit, in fact, I'm seeing us hitting sort of a point of diminishing returns from the current AI use cases. Because why are we predicting things with AI? Well, we're doing it so that we can take some action. If AI doesn't lead to some action in the real world, then what's the point after all? And what happens before that action is some decision we make. And so almost every AI system that we look at lives within a larger decision context where some decision that we're making turns into some action which will then result in some outcome. And whether we're deciding, what to do in some conflict situation or how to solve world hunger, whenever we're trying to solve those kinds of problems, we're thinking through a decision we might make that propagates through a complex system that might have feedback loops and governing circuits. And yeah, there might be a little AI in there that tells you how to go from one step to the next. But I think if we're looking at the cutting edge of AI, this larger context of being the actions that the AI enables and the decisions, the thought processes that people go through as they're making those decisions to take those actions, that's very clearly that causal modeling, complex systems modeling is the next really big thing in AI, which is being called decision intelligence, which is kind of cool because we've got AI, artificial intelligence, BI, business intelligence, CI, collaborative intelligence, and now we've got DI.
I want to work on ZI. I want to
ZI.
get ahead of the curve.
You can get to Z.
I can see where this pattern's going.
But when you do decision intelligence, the number of use cases just explodes. And instead of just YouTube and Google and a few other like advertising use cases, you can start getting into these really, why aren't we solving the really hard, wicked problems with AI? It's because we haven't yet done this context question that you're asking about around actions and outcomes in complex systems.
Well, and it seems that we're still working on fairly task-specific kinds of intelligence rather than a real general intelligence.
Mm-hmm. That's definitely true. I mean, it's and it also still takes way too much handcrafted artistry to make these systems really work well end to end. So the core algorithms are only a very small piece of the whole puzzle. One thing that gives me optimism that I think is a fair candidate for the bleeding edge of AI are these so-called AutoML systems, where now, partly because we have so much more computational capacity thanks to specialized chips and so forth, a lot of times we can take a system and sort of adapt it on the fly. So for example, if you've got a specific computer vision thing for your domain, like you're trying to take drone photos of crops and figure something out or whatever else it is. You may not have a giant data set, but we can sort of bootstrap with a general neural net that's learned general image recognition, and then with a much smaller training data set from yours, sort of adapt the model on the fly to kind of specialize the top layers for your particular use case.
Inductive transfer.
And yeah, transfer learning, exactly. And in many cases, we can take custom models and train them, figure out the parameters, figure out the structure almost completely on the fly, basically by having the machine use a neural net on itself to try different things and kind of guess what tweaks are likely to make it better, kind of like you do when you're iterating on a system to get it well. And the advantage of that is a far broader number of people can take advantage of AI systems than could today. So if you're almost every company, if you're even a small business, you've got some amount of data on your customers or your operations or something that you want to be able to make smarter decisions about. But to be able to hire really talented people and invest in building a whole system is a pretty high bar. But increasingly, if the systems can kind of tune themselves, I think you'll see a lot more people be able to take advantage of that.
Yeah, it's funny. That illustrates an important point. I wrote the first book on transfer learning with Sebastian Thrun back in '96.
I've read
it. You read it?
Yeah.
Whoa, I'm impressed. And it's a hard book, and it costs $134. Anyway, and it's only today that algorithm and those techniques are actually making it out into practical reality. And so that kind of illustrates a more general pattern. Guys, we do not need more algorithms. The bottleneck is getting these algorithms out into usage. And we don't have a software engineering discipline for AI yet. And that's the bleeding edge for the next 3 to 5 years. That's what's going to get AI used to really, generate tens of millions of new revenues or cost savings or whatever at traditional Fortune 500 companies like, Grainger or GTE or places like that. And there's a giant opportunity. So the Googles and the YouTubes and all of us little tech folks here in Silicon Valley, that's, we like to think that's the whole universe, but it's not. And so to me, the next 3 to 5 years is taking these algorithms like transfer and others that have been invented over the last 3 or 4 decades and doing the good software engineering, practical requirement solicitation work to learn how to get AI into those situations.
It seems like a lot of the work that's taking place is to try to overcome some of the asymptotes that we're coming up against, primarily energy, or including energy, and basically getting down to the hardware, which is really kind of your specialty, Tom.
Right.
So are we bumping up against a hardware wall?
We've been bumping up against it since 2005 when we hit the power wall with the Pentium 4 Prescott, which when clocked to its design frequency, dissipated 200 watts per square centimeter. I know most people are number illiterate when it comes to things like this, but that's the same power density as an operating nuclear reactor core.
Ooh, not a good thing.
Not a good thing. And if you look at frequency over time of processors, it's leveled out. That's the power wall. And it is true that we can use things like the TPU to accelerate, but the TPU is just a one-time bump, right? It just gets us to, and now after we get that extra compute power, how do we move on beyond that? So I think the real answer to that is we have to go back to fundamentals and think about what we're trying to model. Instead of trying to simulate the brain on top of something that was really designed to do, well, let's be honest, the computer was designed to do artillery computation. Mm-hmm. We should go back to fundamentals and look at a different compute model for how to do the kinds of algorithms that you two are talking about.
So we were talking earlier, and it sounded to me like you're like this generation's Danny Hillis. Are you doing like the new connection machine?
Oh, don't compare me to Denny. Although that giant clock was really cool.
I know, right?
Yeah. How do you know if it's well, anyway.
Is it massively parallel? Is that where you're going?
Yeah, I believe that's one aspect is massive parallelism. Another aspect is analog computing. And whenever I say that, it scares people. They think about op amps and the like. But I don't mean that. I mean just I've used the term analogous computing as well. So because analog makes so many people think of analog electronics. But anywhere where you can find the problem is solved naturally by a natural process, you can use that to compute. Another example that's becoming really predominant in a small community, but we're a growing community, in the interface between the neuromorphic and the neuroscience communities, this idea that the brain fundamentally uses an open thermodynamic compute model. I like to say the thing, if you watch a a sunflower track the sun, you don't conclude there's an intelligence there. You conclude that there's something going on that's really just taking energy and channeling it to find a new equilibrium. Well, why did we think that nature stopped using that technique at our skull? Okay, it's clear as we go deeper and deeper into neuroscience that there's still the properties of thermodynamics seem to be explaining quite a lot of the phenomena. And that's far more efficient than quantizing everything and taking every transistor as an amplifier, right? And taking this poor amplifier and forcing it to be all on or zero. So I think that the next path forward is really analogous computing and getting closer to neuroscience. And that'll give us orders of magnitude better efficiency.
So we've got like this impedance mismatch representationally between efficient compute and how we're currently instantiating
and you know,
that.
and that's our fault. In the hardware industry, that's our fault because, well, we made everything nice and comfortable. All you had to do was sit back and with the combo of Moore's law and Denard scaling,
just turn the
bingo.
crank. Yeah,
It'll, you know, people would say, hey, things are going to get faster in a year and a half, so why do we have to worry about it? Well, not so much anymore. So it's time to worry about it.
So modeling neural networks, not just from sort of a logical standpoint, but actually from a physiological standpoint, or how they operate?
So let me not say, I want to distinguish neuromorphic from neuroscience. That neuromorphic is really this field where we went back and we looked at how the brain worked, and I think we were talking about 50 years ago, almost 70 years ago, and we checkpointed it. And we've stuck with variations on that model, which is this multi-level perceptron model.
It's like a cartoon of a neuron. It's got like 4 parts, but a real neuron's got like 1,000 parts.
Exactly.
But we're still using it, right?
Yeah. And it's worked pretty
amazing
good.
how far we've gotten,
I would
actually.
never have thought that simple model went so far.
But the question is that, okay, is it time to go back and re-checkpoint? And I think it is. But then when we checkpoint, we're still going to come up with a new model of computation. We're not, this isn't about rebuilding the human brain. I don't think computing was ever about creating the human brain because we built computers to do exactly what we can't do well. This is about trying to use a new model of computation and see where it takes us.
So is understanding how animals communicate, is that going to give us some different models of language or different, you know, sort of logical models to use in computing?
Absolutely. I mean, what are we doing right now? There's invisible words coming out of my mouth and going through this room and hitting your ears, right? Animals communicate multimodality. They're visual, they're behavioral, it's much more, a motor kind of communication. And, elementary school teachers know that this is like the worst way of learning and communicating. We're all sitting here without our hands moving. And we're much smarter when we're standing up and moving around. And animals know that. And, as we move forward to new modes of analyzing hard problems, I think we'll be moving beyond the auditory sequential, Broca's area kind of thinking to what animals do and whales do, which is, this whole brain visual motor kind of thinking, especially again for these wicked problems where there's a lot of complexity and feedback loops. We cannot grok those with the words and the text that we're using today, for sure.
So I had originally intended to leave a lot of time for questions because I thought it was an interesting enough subject that I really wanted to get a lot of input from the group. Turns out we've got about a little over 5 minutes left, so I am going to turn to some questions. Because the light's in my eye, I can't identify faces, but let's start over here.
Mark Mahan, do some or many of the AI algorithms lend themselves to quantum computing?
Yes, actually, there's a whole class of optimization problems that are very amenable to quantum, especially the sort of gradient descent type algorithms. You can often get there much faster with quantum computing. So in fact, a lot of the quantum computing work that's being done at Google is specifically around quantum AI and trying to have much faster kind of optimization. So
you're talking about quantum annealing, right?
Yeah.
Boltzmann machines, yeah.
Yeah, okay. Yeah, but that isn't real quantum, would be what my friends say. So if you go to gate level quantum, right, I think there's also an argument to be made that you can build actually multi-level perceptrons in gate level quantum. And there are people looking at that as well.
Yeah.
In other words, the simple answer is yes.
Any idea how that attacks the energy problem?
No. Okay.
Depends how much you're spending to super cool the.
I'll tell you.
These are not low energy devices.
But we heard from Dennis Bushnell, right? If you put them in space, then maybe that's actually a pretty good way to keep them cooled and keep them from decohering.
We still need a signal generator for every single qubit in the way we're doing it today, which means, yeah, it might be that the actual quantum computer isn't consuming much power, but the back room, I have these friends in Keysight, this is the old Agilent, right? They love quantum computing because they're selling these instruments right, left, and center. So what the hidden thing about quantum computing isn't the quantum computer, it's what's in the back room.
Okay.
Great. Curtis, I'm not an AI person, but I get the sense that basically with more data you can, from lots and lots of people and deep neural nets, you can get a sense of what you're calling AI. How are you able to extract out potential bias or things that are not obvious in the data?
That's
Any
super
thoughts on-
important. I mean, there was just a recent story with Amazon about how they were trying to automate some of their hiring practices, and they were sort of biased in their pipeline around gender, and it was getting reflected in the models. And ML fairness is a huge topic right now, rightly so, because if you're not careful, if you have biases, even if they're unintentional biases in your training data or in your setup, those biases will just get statistically reflected in the model. And so you have to be very active. There's a whole field of study on how you sort of actively counteract that by a bunch of different statistical measurements to sort of make sure that you're not letting that stuff creep in.
And,
But yeah,
and
it's a
one,
big area.
one of the keys to add to that, to unify a few of these other things, is to build the decision model around just the AI model so that you understand how the decision making that's being based on that AI. And that decision model should be visual because it's often quite complex. And the reason we miss that bias is what I was talking about earlier. We're all talking in text. And the complexity of these things is big enough that we need to move not just to pictures to show how those models fit together, but moving in interactive pictures. So we're really driving this deep intuition about how the decisions are interacting with the AI, which might lead to bias and feedback and all of that. So this whole next layer is really innately trying to address exactly that
So
bias.
visualization is really going to be key in the future.
Explainability more generally. I think that's another real frontier topic in AI is how
that's
do
a good
you
point.
get either build explainability into the models based on the sort of the shape of how you learn them, or retroactively, like we did with Deep Dream, go in and try to figure out what it is this black box actually learned.
Okay, thank you.
Lorien, how do you deal with the nefarious trainer issue, right? I mean, I have friends in three-letter agencies that worry about, yes, it can make decisions, but how much can we trust those decisions, and how can we guarantee that there wasn't some nefarious data placed in the training set?
There is no technology that does that because the understanding of how nefarious trainers work is a human understanding. It's a systems understanding that nefarious trainers exist. Now, you can have technology that supports you. In other words, if you see historical nefarious stuff, you can find signatures of that, or you can see anomalies. But fundamentally, in order to understand that, you need a human in the loop. And again, that's the theme we're talking about. Most of the current AI use cases are fully autonomous. And there's an explosion of things we can do when we get humans into that decision-making loop, where you have some human expertise about policing and how nefarious people work and how they interact. So it's a hand-in-hand sort of partnership to solve those kinds of problems.
So we're almost out of time. To wrap things up here, I'd like to throw out to each of you, again, in sort of this 3 to 5 year time horizon, where do you think are the areas of greatest opportunity? What's going to be happening in the next 3 to 5 years that you're most excited to tell these people about, or that they're going to be most excited to see when it happens? Tom?
Well, for me, I want to see AI move to the edge, but to move it to the edge, it means it has to become fundamentally more power efficient. So I think that might be the first place where we try analog techniques to do inferencing. And once we get there, I think it'll be an example where it's sort of, I gave the cloud panel a hard time. It'll be an example where we decouple some of the computation from the cloud. So I'm really excited about the IoT edge using inferencing.
I think in the next 3 to 5 years, AI gets real. And that means that the whole hype about AGI, we start to think a little bit more clearly and know how to avoid some of this unwarranted fear that the press likes to froth up. And we learn how to look through that froth to what's real. And what's real are decisions we make, and how those decisions lead to actions, and how those actions lead to outcomes. And bringing humans into that loop, and then software engineering is what, we usually bring in engineering disciplines when some scientific technology is ready for widespread deployment, and that's what's going to happen in the next 3 to 5 years. It's going to be tremendously exciting. It's like 1956 all over again, when coding was just coders, and then we had engineering disciplines, and so it's really neat.
Joseph?
Yeah, I'd tie those together and just say I think we're on the brink of AI enabling us to have really truly ambient computing, where you just kind of interact with your world and you can talk to it and it knows what you want and it can get things done for you. And the AI being on device, having sufficient training data, being personalized enough, having all these devices work together is what's going to really enable that. And I see that so clearly. I have 2 little kids, and they've just grown up in this world where they can say, hey Google, turn on the Christmas tree lights, and they like magically come on, and they can say, hey, play this show on the TV, and it just works, and they can ask a question and just get an answer. And even as primitive in some ways as our current technology is, it already is kind of a phase change in how they think about technology and how they interact with technology, and it's just going to get better and better, and I think it's going to unlock it not just for people who wouldn't want to use a mouse and cursor, but for all of us in many more circumstances where today there's just sort of too much friction.
That's a perfect note to end on. Thanks.
Thanks, everyone.
Thank you.